Design and Management webinar series. The System Design and Management program is a mid-career master's degree program that's jointly offered by MIT School of Engineering and the MIT Sloan School of Management. The System Design and Management program provides a systems thinking perspective that integrates management, technology, and social sciences to address rapidly accelerating complexity and change in today's global markets. Graduates earn a Master of Science degree in Engineering and Management. The SDM program also offers a one-year certificate in systems and product development. We're pleased to have Eric Ward present today on creating products, services, and infrastructure for a spacefaring economy. Eric Ward is a systems architect who believes that cultivating the private space industry is the next step to expanding humanity's reach beyond Earth. In addition to publishing several technical documents on system architecture and the space industry, he's been featured in Fast Company and Geek Time. He also co-founded the MIT New Space Age Conference. Ward recently earned a master's degree in Engineering and Management from MIT through the SDM program. He also holds a bachelor's degree in Mechanical Engineering from Oregon State University. Eric will present for roughly 45 minutes, and we'll open up the webinar for questions. Please use the chat feature to ask questions, and we'll respond to as many as possible. Please join me in welcoming Eric Ward for his talk today.
Thank you very much, Joan. I'm glad to be here, glad to present to you guys. So why don't we get into it? I'll be talking about, like Joan mentioned, creating product, service, and infrastructure for a spacefaring economy. And I use the word spacefaring here pretty intentionally. We'll get into that a little bit more. But I'd like to start out by talking about kind of the reasons to become spacefaring. Why should we go into space? I think this is important because it can really inform how we think about the future of spaceflight based on kind of our current motivations. And once we talk about that for a little bit and take a look at the system, we'll get into the gaps in the infrastructure, products, and services and see how we can, in the current time, assist that progress to becoming a spacefaring society. And so, as I talk about this, I'd say spacefaring. I don't mean creating products for the new space economy, but really for a spacefaring economy. What it will look like in the future when humanity is in space. And like I mentioned, the reasons to become spacefaring I think are very important because it can really inform how we think about this on a systems level. And so these reasons can kind of be lumped into four categories you can see here, and we'll go through all of them. The sort of curiosity, people want to know what's out there. We're curious to see what's around the corner and have been throughout humans' history. Science is another important reason. We can learn a lot about our solar system, our planets, and other things, even how life arises if we can find extraterrestrial life. There are a lot of questions that can be answered by getting off the planet. There's this idea of a backup plan for humanity, and we'll get more into that later. Elon Musk and Stephen Hawking have talked about that a lot recently. And of course, what I think is very important is a pillar of growth in sort of a trophic economy that we have is kind of expanding our economic horizons. So to start out with, curiosity and human spirit is a very important reason. I think this is something that motivates a lot of space enthusiasts and professionals, and is really a key component to kind of the human spirit is this curiosity and this drive to get out there and explore. As Gene Roddenberry said, space is the final frontier. I would posit that it's the next frontier because there's a bunch of them. There's Earth orbit, there's the solar system, there's the galactic arm, etc. And these are all each different frontiers, but there's not a lot of land left on the planet to explore, and exploration is something that humans are very good at. The flip side of that is that just because we're curious isn't necessarily a great reason to go to Congress and ask for more money for NASA, for example, or really provide an excuse to get out there. And but beyond that curiosity, there are some more sort of pragmatic, even though still somewhat philosophical reasons. Dr. Klein suggested that we have an opportunity by colonizing another planet to experience a fresh canvas in a way, to perhaps leave a lot of the sort of cultural baggage that we have here on Earth behind and start new. And in some ways that could be worse. We could bring the bad stuff with us and leave the good, but it's entirely possible that we could go colonize a new planet. We could leave a lot of negativity behind and really grow as a culture, as a species. And the argument there is that that there's this opportunity to potentially to grow in a way that we cannot do if we stay on Earth. And Dr. Klein even went as far to say we have a moral imperative to take that opportunity. And kind of on a similar vein, you have people like Stapleton, for example, in his quote Interplanetary Man. He argued that there is this potential to really alter the human culture, our intellectual potential, and even our diversity by having people who live on Mars. That creates a very different situation, and even the potential goes as far as speciation, that humans are somewhat homogeneous now, but if people are living, breeding, dying on different planets, we can really grow as a species. And so these are what you might call quote aspirational motives that really, I think, drive a lot of space enthusiasts and space professionals personally, and probably a lot of you that are here listening. But they do, I think, in some ways, really create a core of what drives the industry forward as we all sort of dream about space, but are difficult in a way to justify big economic investments, for example, and so it doesn't really create the entire picture. So as we go on, there's like I mentioned, the science, the sort of understanding the universe thing, and you can see the Curiosity rover's selfie there on the right. They can gather a lot of science through this sort of robotic exploration. We have had very useful insights from Curiosity, from Opportunity and Spirit and Pathfinder rovers. There is a limitation, though, to what a robot can do. With AI that can help, but there's a communication lag between the outer planets and Earth. And beyond that, there's really a undeniable benefit to having boots on the ground, to being a human, a scientist on the surface of Mars, doing the research yourself. You can really react to an environment and have this sort of flexible line of inquiry that a robot can't provide. And so, while robotic exploration is a lot cheaper than sending humans, and it is very powerful for science, there are undeniable benefits to become a spacefaring species, and that we can send people out there to explore. There is, again, an issue here, because the future value of scientific research is very difficult to quantify and even more difficult to predict. The sort of most tangible way to quantify that scientific research is through tracking, for example, papers that come out of a research project, or the citations to those original papers. Although, that sort of tracks the propagation of scientific research to more research, and not necessarily the sort of tangible, pragmatic benefits of the science. And then, of course, it's even harder to estimate. If we send another probe to Mars, how many papers are we going to get out of that? How many times are those papers going to be cited? And there's really no way to know, and that's why, in some ways, it's exploration and inquiry. And so, this again is a big driver. This is one of NASA's core tenets, is to do this scientific research, this exploration. But again, it can be difficult to predict as you look into the future, and as you try to build a system of a spacefaring society. It's difficult to predict how we will actually benefit from that. So the third reason to become a spacefaring society is to have a backup plan for humanity. And you've probably heard about this recently. Elon Musk and Stephen Hawking are big proponents of this. And they say that planetary colonization is essential to the survival of the species, basically, especially when you're looking at these potential planetary extinction level events, such as the asteroid that wiped out the dinosaurs. And even as you look, to the future of global warming, for example, that could, potentially turn out very bad and be a very large, tangible threat to the existence of humanity. And this one, personally, I feel like it's a little bit pessimistic. You're kind of looking in the face of a doomsday scenario and what can we do? But the more I research it, the more I think that it is a very important thing to consider. There are sort of two considerations. We'll get into technology windows later, but another one to remember is that if you're looking at an extinction event on Earth, that means that your extraterrestrial colony on, for example, Mars, needs to be self-sufficient. And that a self-sufficient colony that can survive indefinitely without support from Earth is a very difficult problem compared to even a permanent colony that can still interact economically or through resources or even just communication to and from Earth. And so while we could create a colony on Mars, creating a colony that is necessarily capable of surviving if Earth is destroyed or humanity on Earth is destroyed, is a very different problem. And so that's, I think, an interesting consideration when you think about humanity's backup plan. And I'll get into technology windows in just a second, which is, I think, a very fascinating argument for it. But there are people who, interestingly, argue that it is unethical not to colonize another planet and even to continue propagating humanity through at least our local region of space, through the galactic arm, up to the point that we encounter other sentient, intelligent life. Because at the moment, we are the only intelligent, sentient life form capable of spaceflight in the universe that we know of. And the argument here is that it would be unethical for us not to propagate this uniqueness throughout the universe, at least until we encounter, other spacefaring intelligent life. And then you kind of come up to this quandary of, how does that interaction happen? If our imperative has been to expand just because we exist, and then we find someone else who exists, how do we interact? But I do think it is interesting, kind of from an ethical standpoint, to consider that allowing humanity to become extinct could be unethical for us. So I mentioned technology windows, and I do want to talk about that a little bit, because this is an important consideration when you think about a backup plan. You can see in this chart, if you look on the x-axis, that is time, and over the centuries, you could see we get more and more technological capabilities. We can, start by irrigating our fields that we learned how to do, in ancient Mesopotamia, and the ability to build arches allowed us aqueducts to irrigate from far distances, to build bigger structures. And now we have automobiles who are used to ride horses or horse-drawn carriages, etc. And so, I'm drawing this line. We've got this general upward trend, and a lot of people, me included, as we kind of think about the past and the future, tend to assume that it's this, gradual, steady incline to more and more capability. The argument here goes that we actually, don't have this sort of steady incline, but there are moments where our technological capability as, kind of a greater collective of humanity decreases. And so I believe Elon Musk talked about, for example, the sacking of Rome and the fall of the Roman Empire. For many centuries, we lost the ability to build aqueducts and have this long distance irrigation. And he brings up as well, in the early 1900s, people were talking about this heralding of a new age of peace and prosperity, and then we had World War I, World War II, and the regional conflicts of the Cold War, and these events that maybe not completely destroyed the knowledge of how to build an aqueduct, for example, but possibly the economic and social impetus to do so, that sort of greater ability. And so if you look at, for example, a theoretical level of spacefaring capability that we right now can go into space. We can use spacecraft to explore the moon, low Earth orbit, and as many people would argue, we have the technological ability now to at least put an outpost on Mars, although it would be expensive. And so we're, for example, at this point right here, where we've gained the capability to cross this sort of green line into spacefaring species. The argument goes that we can't really predict the future. If there is, for example, a World War III, while we might not lose the understanding of rocketry or the technological designs of a spacecraft, we might go into a very large recession that takes a long time to recover from, where humanity as a species just won't have the economic muscle to send people to Mars and colonize Mars. And so, maybe it's not a world war, maybe it's an epidemic, or maybe, global warming is such a problem that we have to spend our money in all these other places, etc. But the idea is that, we don't know what's going to happen on that level in the near-term future. And so we might have this very short window for now where we can put a colony on another planet. And if we dip below that capability for some extended period of time, and we have an extinction level event during this slump, we have missed the window of technological capability to create this backup plan. And so I think this is an important consideration when you think about this backup plan for humanity. It's not just that we're fighting against that sort of statistical occurrence of an extinction level event, but we're also fighting against the potential occurrence of a regression in our technological capability. And so as you think about that backup plan, there are some sort of temporal pressure to do that sooner rather than later. And then finally, I want to talk about these sort of economic reasons and growth. And we have this trophic economy, which is perhaps a bit of a misnomer. The trophic, I believe, specifically relates to nutrition, but you can think of the trophic pyramid of nutrition, of food, of how different species interact with each other, and really draw that parallel to how our economy works. And the idea here is that as a trophic economy, or as a food pyramid, for example, you have producers on the bottom level that take essentially sunlight and turn it into vegetables and plants. You have primary consumers that eat those plants. You have then secondary consumers, which eat the primary consumers, and so on. And so you have, like, for example, on this chart, you have a quaternary consumer, a hawk, that eats snakes, that eats mice that eat bug, that eat plants, etc. Or maybe not mice, but the point remains that hawk couldn't exist with all the pillars underneath it, even if it's only concerned with snakes and getting its food from snakes. That foundation of plants and vegetables allows the hawk to survive. And in a similar way is how our economy works, where we have these fundamental pillar of natural resources that we need to gather and use. And in order for a group to increase their GDP or their group's annual productivity, they need to find more natural resources or more efficient ways to utilize the natural resources they have. And I think this is important to think of it like this, because sometimes I know that if I fall prey to this, we think of a lot of advances in current technology tend to be in this sort of knowledge economy at the top of this pyramid, where we're making advancements in software or usability, or artificial intelligence, for example, doesn't necessarily rely on growing more lumber. But these are all just ways to more efficiently use the natural resources we have, and humans as physical beings and our economy as a whole really stands on the pillar of natural resources. And so in order to grow humanity as a whole, we need to explore unknown reaches of our environment, including, importantly, space, and discover new resources and ways to utilize those resources. And that means that we need to get off the planet. And I have this graph here. It's maybe a little bit of a tangent, but I think it does help to illustrate the point. This is the Carkovs Scale, which is a way to kind of, in some ways in a sci-fi manner, but it provides, I think, a good thought experiment to categorize a species. So you might have a type 1 species that can use and store, essentially gather, store, and use all of the energy of its planet. A type 2 would be one that can use, gather, store, and use all of the energy in its solar system, or of the sun particularly. A type 3 might be a civilization that can use all of the energy of its galaxy, all of the suns. And that seems sci-fi, it's, maybe a long way off, but you can extend the scale backwards. And maybe a type 0 is a civilization that can use all of the energy available on the surface of its planet. And a type -1 perhaps is a continent, or down to maybe even a valley. And the analogy remains, humanity started out, or even pockets of civilization might start out in a valley and use all of the natural resources there, and realize that as they grow and get become a larger group of people, they need to move on beyond the valley to get more lumber and more arable land, etc. And so, while we're not up there in a type 1, 2, 3 civilization yet, I think it's very important to understand that our economy is built in a way that we fundamentally rely on a sort of inflationary growth of the economy. And because that is founded on natural resources, we do have, if not immediately, a short-term imperative to grow beyond the surface of the planet. And so that kind of wraps up the sort of the four, what I would say, major reasons categorically for becoming a spacefaring society. And these are all, in a way, quite forward-looking and may not be sort of immediate concerns, but they will inform how we understand this system as a whole. And so when we look at that, we go beyond just why should we become spacefaring and move towards that. We've got to think, how do we get there? I've got that little maybe SAT comparison there. A spacecraft to a watercraft as a spaceship is to an ocean-going ship. We use it in the industry, we talk about our spacecraft. Spaceships are usually a word you hear from sci-fi. That's not just because it's a media expression, but because the technology that we're sending into space are these sort of short duration, close vicinity spacecraft. And the question is, how do we get to spaceships? How do we get to these, the technology level, the infrastructure to support, maybe not ocean going, but solar system going, long duration voyages that can, really support those other kinds of activities. And so when you think about that, and we'll tie in the reasons here in a second, what I've done here is draw up a relatively simple systems diagram of the current state of spaceflight. And so you've got, this is relatively high level a system description as well, but you've got traditional rocketry kind of here in the middle, and that launches traditional satellites which do broadcast data to consumers, essentially, among other things. And you've got the launch of spacecraft, which resupply our space station, and you've got the launch of exploration craft, and both space station and exploration craft send data back to scientists. And then we have this relatively new section here of CubeSats, but you can see that they kind of create a triangle with traditional satellites that they do rideshare with, and they do this brokered launch in traditional rocketry. So they don't interact directly with the traditional rockets, but actually sort of have this double-sided market where they piggyback on a traditional satellite's launch. And right now, CubeSats provide observations to consumers, and that's about it. And so as you look at this current system, you can kind of see we're doing spacecraft, we're looking at exploration craft. and we're looking at the current state of the industry. Now, we've discussed 4 different reasons to go to space. And importantly, and I mentioned this pillar of growth in the trophic society, which is kind of the one I've chosen to focus on. And while I'm really motivated by these aspirational ideas as well, I feel like this pillar of growth in a trophic society is a fundamental reason in the short term to start looking at the space economy. And so I've, in the second slide, altered the systems diagram to include what you might call a quote preferred future, to borrow a term from the futurism methodology. This might be a preferred future that's based on the core motivation of economic growth and growing our economic sphere of influence beyond the surface of the planet. And so as you look at the system diagram, we've got sort of the same core here, but we've added MicroLaunch that it does dedicated launch for CubeSats. And CubeSats, of course, are these small satellites about the size of a bag of flour, for example. They're a lot cheaper to build than these traditional satellites. And so they can provide, you can send up a lot more satellites for the same amount of money, or you can send up the same amount of satellites for a lot less money. So, this really growing industry. Well, MicroLaunch could enable them to get to space on their own without being tied to the traditional rocketry and traditional satellites. And then we've got CubeSats, for example, providing Internet of Things communication and data to consumers, where traditional satellites might not have the bandwidth to do that. And then, for example, if you take a look over here, we've got fuel depots in space that might refuel exploration craft and space stations. And with the advent of fuel depots, we could add in human exploration, because with a fuel depot in space, we now have the capability to send a human all the way to Mars without spending drastically more money. And I'll get a little bit later, I'll get into the math of that. And then importantly, you have some key connections and components here that are directly related to this economic growth and the acquisition and use of natural resources. In the upper left corner, you'll notice we've added mining operations that supply the fuel depots, but also provide platinum element group metals to consumers on the planet. And right here, we've gathered additional natural resources that we can now use to build our computers or even jewelry. And then, space stations, and it doesn't say it here, but that can be expanded from one scientific-based space station to perhaps multiple space stations that do other things, like provide microgravity manufacturing to heavy industry or provide tourism to consumers. And so I mentioned this is a little bit simplified, but I think it does importantly illustrate this point of moving from the current state into what we look at as a preferred future based on our main motivation to become spacefaring. And so I've highlighted in this slide all of those changes, and we'll get into them in a little bit, because we can see quite tangibly here what the gaps are between the current state of the space industry and what products, infrastructure, and services we need to create to become a spacefaring economy. And I'm going to get into a lot of these and some of the major gaps here, and I've mentioned many of them before. So there's the importance of CubeSats, and I'll talk why those become very important and what the gaps are that we saw here in the comparison between the current and future states. I'll talk about the rocket equation, and that gets into ISRU, or in-space resource utilization, from sort of 2 angles. And these are some of the major gaps that we need to fill by infrastructure and products and services in order to become a spacefaring society founded on economic growth. So CubeSats are really becoming the workhorse of the space economy, and this is some data from SpaceWorks, and this is, I believe, backed up by Frost and Sullivan and the Torrey Group. These predictions for the growth of the CubeSat market are all pretty consistent. And kind of as I mentioned before, these CubeSats are small satellites about the size of a bag of flour, and they have, you could say, reduced capability compared to a traditional satellite. They don't stay in orbit for as long. They don't have the ability to do station keeping, to stay in the right place. They're usually very close to Earth, and so the thin atmosphere up there drags them down, and they eventually burn up. And they also have, a lot less redundancy, but they tend to use off-the-shelf electronics and focus on a lot of other Silicon Valley innovations like agile product development. And while they're less reliable, they're also so significantly cheaper that, or so much significantly less expensive that you can afford to send up multiple satellites and have a handful of them fail, and you're still using less money. And this also importantly opens up new paradigms of satellite operation, where when satellites cost hundreds of millions of dollars and were the size of a school bus or a truck, you couldn't send much more than a handful into space. But when they're, tens to hundreds of thousands of dollars and are so small and easy to get up there, you can send hundreds of satellites into space, which means you can do very different things with the data that you're collecting, for example. So the big gap here, this problem, and many companies would like to send hundreds and hundreds of these satellites into space. The problem is that they don't have a way to get there. You can see some lead measures like this orange line here, attendance in the SmallSat conference, which has been going on since I believe the mid-80s, and has just recently spiked in attendance based on these companies and people interested in using micro nano satellites like CubeSats to do business in space. But you can see some of the data from the previous slide and these projections tapering off to the right here. And most industry analysts agree that the growth of the CubeSat market is capped by the availability of launches. I mentioned CubeSats don't have their own rockets to send them into space. They share rides with traditional satellites. And so MicroLaunch becomes this large gap. And if we agree that CubeSats, just by the way that they're inexpensive and we could send so many of them up there, as we agree that they can become a workhorse of the economy and really change the way we think about doing business in space, we really need to be able to give them the infrastructure and support of dedicated launch for these small satellites. And so this is something that I've been working on at Odine Space, and there are other companies with different approaches to it. And one thing that I just quickly like to mention, I don't want to get into a full-blown pitch here, but we believe at Odine Space, and this is something that the STM program has taught me, that MicroLaunch is really going to need some intelligent systems design to be successful, and not just the design of the rocket itself and that system, but the entire integrated business system, including operations and logistics and business models even. Because as these rockets get smaller and smaller, you lose a lot of potential overhead. You can't afford to go to a very expensive launch site, for example, because that's not covered in a multi-million-dollar rocket launch. You've only got a few $1 million perhaps to fit in your overhead. But also because you lose a lot of the potential economies of scale of these very large rockets. And so MicroLaunch, I think, is a very important gap, but it's as a system more than just the rockets and the launches themselves, but also the insurance of these launches, because these launches could be more risky, and while but additionally the consumers, the CubeSat companies, might be able to handle more risk because they're setting up more satellites. And so there's a paradigm shift in the way that insurance might be dealt with. And so there's a lot of other services around MicroLaunch that need to be built up as well. Another gap with CubeSats is communication. And I mentioned in this preferred future, CubeSats might be the the backbone infrastructure for the Internet of Things, where it's conceivable to have a constellation of CubeSats with hundreds of satellites in a low orbit that essentially have communication view over the entire Earth, and that could really enable the Internet of Things. However, these CubeSats need to be able to relay all of the data from those, quote, things back to the cloud, the servers that use that data, and communicate back with the things, as it were. And all of that can't be done with the current infrastructure of essentially communication dishes. And so there's this big gap with how the CubeSats are going to relay this huge quantity of data back to the surface of the Earth. And so there's some interesting projects going on. KitCube from MIT, of course, is working on a laser communication system, and I believe they're actually sending their satellite to lunar orbit and using a laser communication system to precisely download high bandwidth data to essentially a very specific point on Earth with much pointing accuracy. But that technology will also be useful for satellites in Earth orbit that are communicating with quote things on the surface, and then communicating, of course, back to the servers. And so this is an important gap because as we look at that future state of a spacefaring economy, communication, of course, is a backbone of that, and it's something that we have a workable solution now, but we will quickly saturate our communication bandwidth if we don't develop these new products for CubeSat communication. Propulsion is another issue with CubeSats. I did mention, I believe, CubeSats have a much shorter life on orbit. They're close to the surface of the Earth. Generally, they do very low Earth orbits. And so the drag from the thin atmosphere there pulls them back down to the surface and slows them down, essentially, and they eventually burn up in the atmosphere. And because CubeSats are so small, they don't have any mass margin to put in a traditional propulsion system. However, if you're able to put propulsion on satellite, you can enable, like I have here, you can enable a longer orbital life. It can just give itself a boost every once in a while, stay in orbit a lot much longer, and you can get a lot more value out of that satellite. It can allow station keeping, so if it slows down and needs a push in either direction, or it starts getting out of alignment with the constellation or the Earth, having propulsion on it allows it to get back to the right place. And then there's also this idea of rapid orbital spacing. If you're doing MicroLaunch, for example, sending up a dozen or so CubeSats, you don't all need to be in the same spot. You'd like to space them out along the orbit so that they can cover different parts of the Earth, get different data or different communications. Planet Labs, or I believe just Planet now, has proven that you can do that using different drag profiles of the CubeSat, but that takes many months. Putting propulsion on the CubeSat would allow them to very rapidly get to the correct orbits. And so I mentioned here, you can see the picture, that's from Axion Systems, Natalia Brickner and Louis Perna, or excuse me, Natalia Bailey. Both Natalia is a PhD graduate of MIT. Louis is also from MIT. So they started this company out in Cambridge, and they're working on these very small thrusters. They don't have very much power, but what I mentioned here, orbital life, station keeping, even orbital spacing, they're light enough to put on a CubeSat, and they can provide these functions and help the CubeSat approach the capability of a traditional satellite. I think an interesting thing to point out with, and especially as we look at this greater system of spacefaring capability, the propulsion that's on the size class of a CubeSat could have, it doesn't just enable the CubeSat to mimic a traditional satellite. It also allows new ways of using CubeSats. You can have these novel mission profiles, like for example, when KitCube's going to the moon, it needs to be able to inject itself into lunar orbit, and so it needs to be able to have some amount of propulsion. I believe they're a little bit bigger, and they're using a kind of a hybrid traditional propulsion system. But when a CubeSat has propulsion, it can alter its own orbits, and you can start thinking of different mission profiles to use a CubeSat with. Additionally, there's perhaps an idea of flexible operations. If you're able to change your orbit, get farther away from Earth or switch to a different inclination, you can respond to events on the surface or different business models, for example, as your business model changes. And so, importantly, as we look at this gap of CubeSat propulsion, it's not just that there's a technological gap in making CubeSats as capable as traditional satellites, but still cheaper. There's also this way to kind of have this forward-looking perspective and see what else could dedicated propulsion on a CubeSat allow us to do that we couldn't do with traditional satellites anyway. I believe this is another very important one is data, and this is I think can be very interesting as you look at the greater economy, like what a spacefaring economy means. And it's not just hardware and people in space. It's also how we use the knowledge and the data that we got from space, how we use that on Earth. And you can see this company SpaceNode down in the valley has developed the China Satellite Manufacturing Index. And they've used almost entirely satellite data, a lot of data from CubeSats now, in addition to data that they've gotten from traditional satellites, to develop an index of the state of the Chinese manufacturing industry. I think this is very interesting because this is not something that you could have done 10 years ago when we didn't have a bunch of CubeSats in orbit, because the revisit time for traditional satellites, there are very few of them, is on the order of weeks. It might take 2 to 4 weeks for Landsat, for example, to take a picture of the same spot on Earth. But with CubeSats, when you can send hundreds of them up at the same time, you can get revisit times down to the days period. And that allows you to start extracting data that is pragmatically useful for economic analysis, for example. And so I can't point to all of the different spots where data analysis and creating actionable insights from space-based data could be useful. I can't point to all those gaps, but I think it's very important to understand that it's not just the products and the infrastructure of a spacefaring economy that we need to develop, but it's also the services of how we can best leverage a spacefaring economy to grow the terrestrial economy as well. And there are, of course, some other areas that CubeSats, I think, can really shift our economy. There are things like space junk cleanup, satellite servicing, where you've got these multi-million traditional satellites that aren't going to go away, even with CubeSats becoming more and more prevalent. If you can use a $100,000 CubeSat to service and refuel a $600 million traditional satellite, there's a lot of value in that. I do point out here market differentiation is becoming important with CubeSats, and you can see they are part of the current space economy. As the space economy grows, differentiation in CubeSats is becoming more and more important. There are a lot of companies that talk about Earth observation, but there is a limit to how many different companies can be taking the same or similar pictures of the Earth. So CubeSats were a big part of the change between the current state of the space economy in this sort of socio-technical economic system. And CubeSats are an important point of growing into this preferred future of a growing space economy. There are some other big gaps, and I want to take a tangent here to talk a little bit about the tyranny of the rocket equation. If you recall, the rocketry and launch was right in the center of our systems diagram. It really provides the foundation of a space-based economy. You have to be able to get your technology and your people, etc., into space, And as we look towards a economy based on natural resources and the acquisition and use of those, you need to be able to get some of those natural resources back into Earth orbit or back to the surface of the planet. And so rocketry is very important and will continue to be very important as transportation until perhaps we have space elevators or something. But the rocket equation is this fundamental aspect, of course, of rocketry, and people talk about the tyranny of it. You can see in the gap to the right there, there's this logarithmic relationship between your delta V, essentially how much you need to change your velocity or how far you're going and how you're going to come back. And there's this logarithmic ratio between that and your mass ratio, which is essentially just the ratio of the payload, what you're taking into space or bringing back from space, and the dry mass of the spacecraft, and the ratio of that payload mass to the fuel that you burn in your rocket. And so the more payload that you're taking to space, the more stuff you're bringing up there or bringing back, you need an exponentially larger and larger amount of fuel that you're burning to get there. And people talk about it being tyrannical also in that there's essentially no way to get around that. You can design a better engine, and that's about it. For a better mass ratio, or for a larger mass ratio, you just need an exponentially larger amount of fuel. And so this can really create a problem as we're looking to grow our economic sphere of influence off of the surface of the planet. We're fundamentally looking at growing the mass that we send back and forth, and that means an exponentially larger and larger amount of fuel that we need to burn, and fuel is money, essentially. That just means a bigger rocket and a larger cost. And so as tyrannical as it is, it's important in that manner to see what alternative solutions do we have rather than throwing more money at a bigger rocket. And so you can look at skirting the rocket equations. There's gravity assist and over-Earth maneuvers when you're going far away from the planet. You can also reduce mass, but that's we've already talked that there's going to be a fundamental growth in the amount of mass going up and down. You could also reuse mass, and this is more important when you're looking at, for example, a colony on Mars. You might use an Earth-Mars cycler orbit, where you reuse the transportation system that gets humans to and from Mars, the radiation shielding and the life support systems. And that just cycles back and forth between Earth and Mars, and all you have to do is send the humans up and not the humans and their life support every time. And avoiding the rocket equation altogether, though, is going to become increasingly more and more important. And there's essentially one way to do that, and that's in-space resource utilization, also ISRU. Could also mean in situ resource utilization. Here, I think this graph is probably the best way to illustrate it. This was from a project I did during the STM program, and you can see that the red group here to the right is these resupply missions to a colony on the surface of Mars when you're sending everything from the surface of the Earth. These blue, light blue dots are all the architectures that you refuel your oxygen when you're in low Earth orbit. And the pink dots are for refueling your oxygen and hydrogen when you're in low Earth orbit. Oxygen and hydrogen, of course, being the components of a standard rocket, a liquid oxygen, liquid hydrogen rocket. And like we mentioned before, your mass ratio, you need more liquid oxygen, liquid hydrogen, more propellants, exponentially more propellants to send linearly more mass. And so when you're talking about going very far, like to Mars, for example, or to the asteroid belt to gather natural resources and bring it back, if you have the ability to get that extra fuel in space rather than sending up that extra fuel from Earth, you can exponentially reduce the cost of sending your equipment up from Earth, because instead of sending your equipment and your fuel from the surface of the Earth using more fuel, you can just send your equipment up and get that fuel from space. And so in space resource utilization becomes very important to a growing economic sphere of influence. If you can get fuel, in particular, from space and leave it in space, we've really opened up the potential to be a spacefaring species. And so there are some gaps here that bear mentioning, the mining technology in particular, and the ore collection. If you get to, for example, an asteroid that might have platinum element group metals, platinum, rhodium, osmium, things that are quite valuable, used in for example, silicon manufacturing, computer hardware, and many other places. An asteroid might also, for example, be carbonaceous and have up to 10% water in the asteroid, and that's what you'd use to get the hydrogen, oxygen for fuel, and just leave it in space. Extracting that ore from an asteroid is a difficult problem, and there aren't a lot of parallels to on Earth mining because you're doing this in a microgravity environment. You don't have the ore won't fall down towards you. You've got to be able to extract it and collect it using novel technologies. And importantly, as opposed to the CubeSat gaps I mentioned earlier, where there's almost an immediate use for that new technology, developing microgravity mining technology does not have a lot of immediate uses and a lot of parallels on Earth. And so there is a gap. While we need to be developing that now, there is potentially this temporal gap between how we start developing it now and when we're going to be able to essentially make money off of it and pay for that technology investment. Maps are another really important thing. And as mentioned, as Joe mentioned, I'm the CEO of Attendees Engineering, and this is something that we're working on. You need to understand that there are ore-bearing asteroids out there that might have 10% water, or potentially trillions of dollars of osmium or platinum, but we don't know which ones those are. And there are also a lot of asteroids that are essentially valueless, that don't have any of these valuable resources. And importantly, I think the chart on the right really illustrates this by essentially surface area of these circles. We know of 16,000 near-Earth asteroids. Only 770 of those are close enough that they're essentially cheap to get to. The delta V comes up again like the rocket equation. The closer they are, the less mass ratio you need, less fuel you need. Of those, we only have good spectra on 80 of them, and that was obtained for scientific purposes. But the spectra, that understanding of the light that those asteroids are reflecting, that spectra can give us a better idea of whether or not an asteroid is ore-bearing. And very importantly, and what kind of surprised me when I learned this, we only have good orbital data on 25 of those. And so for the 16,000 near-Earth asteroids that humans know of, we have good orbital data that's good enough that we could send a spacecraft to it. For only 25 that we also have good spectra for, that we know what could be on that asteroid. And this is a huge problem if we're going to start mining asteroids in order to bring valuable resources back to Earth, and if we're going to be bringing valuable fuel into space to enable us to go even farther. We need to know about a lot more than 25 potentially valuable asteroids. And finally, as I mentioned this, you develop these maps. There's no one right now that's mining these asteroids. We still need to develop the mining technology. There's potentially even a larger gap temporally between developing these maps, which needs to happen soon, to actually being able to sell them. And so with ISRU in particular, as well as other parts of the greater space economy, there are important gaps in economic tools. I mentioned insurance with MicroLaunch earlier, and mining, for example, even. But there's the potential here for investment modes or financial instruments to really begin to shift their paradigm to match what a spacefaring economy might look like. And importantly, I wanted to mention really quick here that this idea of real or technical options. And so many of you may be familiar with the idea of financial options, where you basically purchase the option to actually buy a financial instrument later. If the value of it goes up, you can exercise the option and buy it for a lower price than you would have otherwise. Has in the last few decades been extended to the idea of real options, where you buy a tangible, real resource, such as a mining field where you might get oil, but you don't begin mining right away, and you're essentially, you have the option over the next decade or two, for example, to begin mining it if the value of that field increases. And I think that this idea can and should be extended to technology as well. As you know, we're looking further and further into the future of what a spacefaring economy might look like. We start getting into the realm of trying to develop technologies now to give us the option of using those technologies in the future, and figuring out how to quantify those, the value of that engineering now in terms of future dollars is an important economic tool that is a gap right now. So you kind of to go back over the system one more time, you know, we're looking here at what would be the high level, quote, preferred future system of a spacefaring economy that's based on the motivation of a growing economy and how natural resources are the pillar of such a growing economy. And I think, you know, of course, and maybe I'll leave it up to the reader to think about how this system might look different if your core motivation is scientific research and exploration rather than economic growth. Maybe human exploration becomes more important, and you know, the transfer of platinum element group metals back to consumers is less important. How does that affect the system? And so, you know, as we look at this and think about this, you know, not the current system or how we can change the current system, but what a future spacefaring economy might look like, I think there are a lot of ways that we can identify the gaps that I've talked about, but also some other gaps that I haven't talked about that maybe you've thought of that haven't occurred to me or anyone else. And so I hope that this was kind of a useful way of looking at the current state of the space industry and what the space industry might look like in so many years, and really how we can get there. And I hope that, you know, some of you I noticed, you know, aren't in the space industry, and hopefully you can kind of take this philosophy back to your industry. I've definitely noticed in the STM program that the tools that we learn there are really applicable to a lot of different industries. So hopefully this was useful, and I think we might have a little bit more time for questions.
Thanks, Eric. We do have a number of questions online. If I can start heading them your way. I've got a question that says, I have a question regarding CubeSats for IoT communication applications. I'm wondering about the power requirements, orbital duty cycle usage, and size of a CubeSat when comparing it with small sats greater than 15 kilograms.
Yeah, so I don't necessarily have a specific number, and it really depends on the satellite design. Usually when I talk about this sort of thing, I like to say, quote, micro and nano satellites. CubeSat is technically a very specific form factor that is made up of 10 by 10 by 10 centimeter cubes, each weighing no more than 1.33 kilograms. And as you get into small sats, you know, maybe greater than 15, I would still possibly call microsatellite, but everybody kind of argues where these lines are. As you depart from the CubeSat, the kind of that strict form factor into, you know, a microsatellite or a small satellite, you really gain a lot of engineering flexibility in how you design that. And so, you know, as Planet Labs is specifically using a CubeSat because they're doing these rideshare launches, they have to use that form factor. You know, they're limited to, you know, a 30 centimeter, you know, 3-unit long camera aperture, lens aperture, essentially, that are focal length, I guess, or a 10 centimeter in diameter maximum aperture. When you go to a small sat, you know, there are some standard buses out there, but you really can design it in whatever way you want. And so, you know, particularly when you're looking at IoT, for example, your system's architecture of that satellite is going to look very different than the architecture of a Earth observing satellite. And so maybe your satellite has these higher energy requirements because you're doing a lot of high-powered communication up and down, and so it has, rather than being covered with solar panels, it might have extendable solar panels on wings, for example. And so that's a question that I can't necessarily answer for you, but it really speaks to the importance of systems architecture, that you kind of answer those top 10 questions of the design of your satellite up front. What are our power requirements? How do changing our power requirements change our capabilities? The capabilities that we want, are those the same as the capabilities we need? And it's possible you might go through that and find that you could actually fit this in a 6-unit CubeSat. The power requirements might not be as great as you initially thought. So I hope that kind of answers your question.
So I have one more that I'll put out there, which is, wouldn't finding a large amount of platinum kill the ROI?
Possibly. That's a very good question. And the short answer is we don't need to worry about that right now, because as much as we might have identified an asteroid in the main asteroid belt that's worth, some quadrillion, I'm not making up a number, we've actually estimated an asteroid that's worth over $1 quadrillion in platinum at current market values. Of course, if we're able to reach out and grab that and bring it to the surface of the Earth, platinum's not valuable anymore. It's not going to happen like that. We're going to start with near-Earth asteroids that might have a little bit of platinum. We'll be increasing the supply of it. There are other elements out there. We might be able to get osmium and rhodium, etc., as well. It will not come all at the same time, and so the financial markets will have the ability to react to this slowly increasing supply of valuable metals from space. I'm not a financial analyst by training, I'm an engineer, and so I don't know exactly how they're going to react, but it's not going to come suddenly enough that the market's going to crash. And I would actually also like to say that as part of the space industry, that's not the only reason to go to space. And we've talked a little about this, and maybe it affects, like I mentioned, more into the exploration motivation for going to space, but almost potentially more valuable to this growing space economy than platinum is water. If you have water in space, you can support space stations, but you can also electrolyze it slowly and turn it into rocket fuel that burns very quickly to go farther into space, or get to and from places quicker, or bring more stuff with you. And so one of the very, I think, important fundamentals of in-space resource utilization is going to be supporting the space economy through mining water and using it as rocket fuel. That's essentially the only way to avoid the rocket equation.
All right, Eric, that's what we have for questions right now. I do want to encourage anybody that's listening. Eric's email address is up on the screen. It's ericward@alum.mit.edu. So if you have further questions, definitely reach out to Eric directly. And Eric, thank you so much for joining us this afternoon. It's always a pleasure to have alums come back and talk, especially on a topic like this that has so much interest out there right now.
Yeah, absolutely. Thank you. That was my pleasure.
We will have this webinar uploaded and online available for rebroadcast later. So if anyone that's on has colleagues that are interested in this area, definitely please feel free to refer them over to the SDM website. And with that, I'll thank everybody for participating today.
Yeah, thank you very much.